Hi, welcome to Exponential Modelling. I hope you're powering your way through this stuff on exponents. Small joke, powers. Anyway, what I did, well, when I read this exponential modelling, I thought, modelling? I'll Google search that. And what I come up with, oh, here we are, 2 models. I think it's a different type of modelling. Oh, well, let's come down and have a look at the type of modelling it is. It's mathematical modelling, where what we do is to try to come up with a formula or maybe a graph, another formula over here, which models or describes a practical situation. And of course the functions that we've been using in exponential work, of course, are these here, where we have a number times a base. We've been calling it b, and here there's another b, and if that b is a fraction like over here, we know that it's going to be an exponential decrease. If it's over here like this, a number greater than 1, it's going to be an increase like we see this one here. So what we're going to look at now is how to use our exponential increasing function, exponential decreasing functions to actually model or describe practical situations. So let's have a look at the idea here for a start. And again, I'm using Pearson's textbook, and it would be good to have that handy by, because I'm using screen clippings from that. And they've summarised what we've done so far here. And they're saying, basically, we're going to think of an exponential function like that the amount after a certain time is the initial amount times a factor raised to the t, if you like. And we're going to say b is always a positive, a is not 0, and b is not 1, but there are 2 conditions. If b is greater than 1, then it's going to be an exponential growth model. So let's put that over here. A at time t is a0 times b to the t. So if this is greater than 1, that's going to be an increasing function. That's going to be increasing. If it's a fraction between 0 and 1, it's going to be a decreasing function. So that's going to, we could call it an exponential decay. It's decay. So there's a couple of words. Just come right up the title here. Exponential growth and decay. An increasing situation, a growing situation for b greater than 1, and a decreasing situation for a b between 0 and 1b is a fraction. Remember, raising a fraction to bigger and bigger powers decreases it. You have a half, square a half is a quarter, cube a half is an eighth. You can see what's happening. And we've looked at that in that first section, 4.1. Okay, so there are our tools. Let's see if we can use them now. So here's a good one to start with. And here we've got bacteria growing in a culture. A sample count of bacteria in a culture indicates that the number of bacteria is doubling every hour. Okay. And given that the estimated count at 1500, that's 3 o'clock in the afternoon, was 12,000, find the estimated starting amount 3 hours early at noon, and write an exponential growth function for the number of bacteria. Oh, that's interesting. So, first of all, we might say, well, we'll take this from over here and say, well, our amount after t hours will be our original times 2 to the t. It's going to double every hour. They say that. So every time you increase t by 1, you will double it. So it's 2 to the t. So what we're going to try and do is to find out what the original amount was by substituting in. It says here 1500 hours means t is 3. So if we call 12 noon, t is 0. So then at 1500 hours, we would say the amount is 12,000, and we don't know the original, but we know there's been 3 hours worth of doubling there. So 12,000 is A naught times 8. Divide both sides by 8. We will find our A naught, which if you do that division, might need a calculator there, is 1500. So we can backtrack to the original amount and therefore have our general formula. The amount after any time is 1500 times 2 to the t. That's going to be a handy formula to use for this particular bacterial culture to predict what it would be in an ongoing way as every hour passes. Okay, so that's what Pearson's is talking about there. You could pause the presentation and look at it. They've worked along the line rather than down the page like this. So let's now have a look at another way of thinking about it. Another way of thinking about it would be to draw up a table and to say, well, at time 0, I don't know how much there was. 1 hour, 2 hours, I don't know. But at 3 hours, the amount after t time was 12,000. If it's doubling every hour, the hour before must have been 6, the hour before must have been 3, and the hour before must have been 1500. That's another way, using a table approach, another form of model, rather than a formula, a table, of finding out the original, when t is naught, the original number of bacteria present. And then there's another way. You could actually plot these points. So you'd start at 12,000, the hour before would have been 6,000, the hour before 3,000, and so on. So you have got, if you like, 3 different ways of modelling that behaviour. And of course this is important to biologists, because if you were to take a culture in a beaker and let's put it on a automatic stirrer, which has a magnet going around, have a plastic coated magnet in there, so we're aerating the culture, let's say at 37 degrees Celsius, and one of the bacteria that people do work with are Escherichia coli, E. coli. And if you do that, it has an almost precise doubling time of 25 minutes, I believe. This one up here, they're talking about, had a doubling time of 1 hour exactly. But what happens in that time? Well, the cell enlarges with the nutrients in the culture there, and the aeration and the heat, and then it starts to form 2 cells, and then finally you have doubled. And this is a pretty precise process if you control the conditions of growth. This is called the doubling time, the time taken to do that. And under controlled circumstances, each type of bacterium has a characteristic doubling time. So this is a well worthwhile model to develop for biologists, for example. Okay, let's go on to another one. And this one is a radioactive decay model. It won't be increasing. We have a radioactive isotope giving out particles here, radioactive particles, high energy particles. And that process is going to lead to a loss of mass of that. And it's going to form a different molecule, a different mass of material is going to be there. That's called a half-life, when you've got only half the mass remaining of that radioactive isotope. So this time we're going to be looking at this sort of model. The amount after t hours is the original times by a half raised to, we have to know the half-life. Because every time there's a certain number of hours or years in radioactive decay quite often, then every number of those years it halves. So here what we're going to do is to say, well, before we can actually raise a half to a power, we have to know the half-life. So we'll actually need to work out the number of half-lives. So here, if we go across to Pearson here, we're saying if t represents the amount of time, the number of half-lives will be t on h, if we call h the half-life. So if we know the half-life, divide by h, so this is really the number of half-lives. I said that, but I didn't actually put that there. So if we have a time and we know the half-life, this is the total number of halvings that will go on, won't it? So let's take an example. If the half-life of a certain material is 25 days and the amount of time has passed since measuring A0 is 75, then how much will be gone? Well, K will be how many half-lives? Well, we had 75 days and half-life is 25. So here, the K value, the number of half-lives that we've seen go by, is 3. So the amount of material will be A0 times how many halvings? There'll be 3. We've got to find out how many halvings there are in 75 days. So we're going to divide our t, our time up here, by the half-life time to know how many halvings have gone on. Because in that time, the amount halves. So that's another application. And you can read that, pause the presentation, read some of that that Pearson's have got there now. So we've got all different sorts of applications for our exponential growth and decay, or increasing and decreasing functions. All right, so let's come down and have a look now at Pearson's summary of that. So this is when you've got an amount of material which is decaying because it's radioactive and it's going to eventually disintegrate and form a different substance. So the amount present is the original amount, and you're going to look at a number of times it halves is the time divided by the half-life. We've got to look at how many halvings we're likely to get. Okay, let's do another example. Let's say we have a radioactive isotope which has a half-life of 50 years. And we want to know how much is present in 1,000 years' time. So the half-life is 50 years. So how many halvings are we going to have? Well, it's our original amount times now how many halvings. It's going to halve every 50 years. How many 50s have we got in 1,000 years? And of course, this is a problem with radioactive waste, that sometimes the half-life is very long and we have to preserve it. Usually now we're thinking about burying it and protecting the environment from it for a long time. So this is the calculation to work out how many halvings there will be, how many half-lives are there in 1,000 years, and that's what we have to raise the half to in our decreasing or decaying function. All right, so let's go on and have a look now at another example. The half-life of radioactive carbon is about 5,730 years. This is why they use it in carbon dating. It's a long-lived isotope, and you can work out from the amount present today how long it might have been there, and therefore find the age of bones and so on. So how much of a 10-gram sample of carbon remains after 15,000 years? So let's start with a formula. We know it's going to be halving. And how many halvings are there? Well, we've got to divide our time in years by 5,730. So this is the number of halvings, or number of half-lives in our time t, because our half-life is 5,730 years. So if we go down the bottom here then, and say after 15,000 years, if we had 10 grams, it would be times by a half this many times. Because how many halvings are there in 15,000 years? There it is. The number of halvings. Because it halves every 5,730 years. So 10 grams would be expected to decay to 1.63 grams in 15,000 years. So you can see the idea. If you could work out the amount of C14 that you expected to be present at any point in time, and then you monitored that over a period, you could estimate the time over which that decreased. Because we're saying that with this particular isotope, it would take 15,000 years for it to go down to 1.63 grams. So it's used in carbon dating, and that's a useful model as well there. Okay, let's come down and let's have a look at this one. This interests a lot of people, compound interest, and it's to do with money, of course. And the idea of compound interest is something's compounding, it's building on itself. If a problem is a compound of compound nature or a compound fracture, it's building on itself. It's more than just a simple one. So it's the sort of thing we might do if we had, for example, $1,000 and we wanted to invest it, and we're not going to take out the interest, so that's going to be part of the growth. And let's say we're going to get 10% per annum. 10% per annum. So after 1 year, we have 1,000 plus 10% of 1,000, which is 100. So it's 1,000 plus that. And then after another year, we're going to have 10% more, which is this time $110. So this time it's $20 we'll have left. Now, can you see that we can, in a single multiplication, change 1,000 to 1,100 by multiplying by 1.01, and here again multiply by 1.01. So what are we doing here? If we wanted to find the amount up here after t years, it would be 1,000 times 1.01, and to however many years it would be. Can you see that? Oh, that's a nice little exponential growth model. And we're going to see this in sequences and series as well, where you have a sequence of numbers, so you can think of this as a sequence of numbers. Let's say we're going to compound every 6 months. Okay, now we're not going to get 10% every 6 months. 10% is per annum. So every 6 months is 5% per month, per 6 months. So we should just get rid of that. We're going to get it per 6 months. Per 6 months. So 5% now is 1/20 of this, so it's 1,050. Or you might be saying, hey, I like this multiplying idea. I have to multiply by 1 to get my 1,000 back again, and plus 0.05, so I'll multiply by 1.05. And then if I do it again, multiply by 1.05, I'll be adding another 5% every month. So my amount after t, now this will have to be, not in months, sorry, this will have to be the number of 6 months, wouldn't it? We're doing it every 6 months. So it'll be 1,000 by 1. Oh, now I've messed this first one up, haven't I? It's 10%, it's not 1.01, it's 1.1. 1.1. 1% is 1.01. So sorry about that, let's just look at that. 1.10. So here 5%, 1.05, and raise it to the t, but this time this would be in 6 months. Okay, so this up here was in years. So the interest rate of 10% 0.10 multiplier has to be matched with the same time. So here the multiplier is 5% every 6 months, so the time up here has to be in 6 months. What about doing it every quarter, 4 times a year? What would happen? Well, 1,000, so this is every quarter or 3 months, which is a quarter of a year. So the equivalent interest rate would be 10% divided by 4 is 2.25%. So we want 1,000, so we'll multiply by 1 plus 2.25%, that's 0.225 will be the multiplier. Every 3 months we'll be multiplying by 1.0225. So the amount present in quarters after this many quarters or 3 months will be 1,000 by 1.0225, because that's our rate per quarter now, and we raise it to the number of quarters here. All right, so can you see the idea? This could be done monthly. So you would have the interest rate divided by 12, and that's usual when you have accounts. It's monthly interest is repaid. So this is an interesting growth model, if you like. So let's come down and have a look at what Pearson's have to say about that one. Here's a compound interest formula. Now, here's the amount after time t. Let's, if we always keep this in years, what do we have to do? Well, it's the original, and A naught here is usually in money terms called the principal, the amount you start with. So we're going to use P there, and look at what they've done in here. Now I put 1 and then added on the interest, but what did I do? The R, let's do the first one, was 10%. So it was just 0.10, not 0.01 as I did originally. And if it's per year, it's over 1, and then we raise it to the number of years. But let's take this in the second case, where it was done twice a year, or every 6 months. We have to divide the interest rate by the number of times per year. And up here, what they're suggesting is NT is the number of periods. So if you keep T in years, you have to multiply by N, the number of times it's done per year. So NT is the number of periods of calculation it will be. So if it's done twice a year, so there's the number of years, you've got to multiply it by 2 to say I'm doing it every 6 months. And if we did it every quarter, that's 4 times a year. So you've got to change the interest rate there to 0.10 divided by 4, doing it 4 times a year. And how in T years, how many interest calculations would you have done? You would have done 4. Okay, so we are going to just watch. First of all, we have to adjust this in here for how many periods. So it's always 1 plus, because you've got your original amount and you've got the added interest adjusted for the period of the year, adjusted for a fraction of the year. But this has got to be how many times. This is the total number of multiplyings that you're doing, multiplyings. So it's the number of years times the number of times during a year that you're going to do it. All right, so that's an interesting formula. It's probably more complicated to look at than what it is to apply. So let's go down now and have a look at an example. An initial amount of €1,000 is deposited in an account earning 5.25%, which is 5.25 interest per year. So here we want to find the amounts in the account after 8 years. So 5.25%, we've got to change that to a decimal. So 0.0525. That's what we'll multiply by to make a 5% increase. Let's do it over 1 year, compounded annually. So what do? The original amount is 1,000, the interest rate is a decimal, and we're going to do it for 8 years. So the first one's easy. It's 1,000, and then it's going to grow once a year, so it's 1.0525, and how many times are you going to do it? 8 years. Look at the next one. Semi-annually, 6 months. 6 months, we did one of those. So it's 1,000. Now the interest rate has to be halved. You're not going to get 10% every 6 months, 5.25% every 6 months. And that's the yearly rate. So you have to divide it by 2 because you're going to do it twice a year. And then you're going to do it for 8 years, but twice a year, don't forget, you'll be doing it 16 times, won't you? 16 times. Let's just come down here a bit. So 16 times. So that would be a different amount. Slightly earning more because you're earning interest more often, and every time you earn interest it's added, and so you'll be getting in the next round interest paid on not just your money, but on their extra interest that they gave you. Quarterly, every 3 months, 4 times a year. So N is 4. So the amount starting is 1,000. You multiply by 1, you always get your 1,000 back, and then you're getting a amount in interest, which is this time only a quarter of the 5.25%, because it's being done 4 times a year. But you've got 8 years, and every year you're doing it 4 times. So that's 32 applications of that multiplying. Monthly, 12 times a year. So it's 1,000. Of course, you've reduced your interest rate to a 1/12 of the original, but you're applying it 12 times. So you're actually in 8 years going to do it 96 times. And then daily is even better. So it's 1,000, but your daily interest rate would be 365 days in a year is 1/365th of that. But you're going to do it many, many times. Because 8 years at 365 days, doing it every day, you're going to be doing many, many calculations there. So it does actually, compared to that, end up with quite a bit more money in there, $16, done in that way. Now that's a fair bit of work. I want you to come over here, and in Pearson's they're using a TI, so their solutions to 4.2, I've left them intact, and because the TI has a similar sort of mode to do this as the Casio, but the Casio here, let's go through it. There's the menu window. You go down to TVM, time value of money, and then you get this window, and you want to choose compound interest F2, and if you do, we get this window. And now let's set this one up, and I'm setting this up to do the quarterly one. So we're going to do this one here on the calculator. So first of all, how many periods of calculation would there be? What is N here? So how many times are you going to do the calculation? Well, you're doing 8 years worth, and it's quarterly, so it's 4 times a year. So you put the number of periods in there. Please note, when you enter the interest rate in the calculators, you put the full interest rate, 5.25%. You don't convert it to the decimal, 0.0525. The calculator will do that for itself. Now, the PV means the present value, the money that you've got. And you always need to put it as a negative. You are losing it, as in accounting terms. It's going away from you into the bank, if you like. There's no payments in. We're just going to leave it there. Future value is naught. Now, this is the line that we want to see the answer to later, but we leave that naught. We want to know what the future value of this money is as it grows. Payments per year, well, we have to put this in the way the calculator is set up, it's 4, and down under this, we won't put it here, is CY, and that has to match. So compound interest payments per year is also 4. So this, in this entry, the one below it, they're set together, is the number of times you're doing it a year. So basically, you don't have to put in the number of years. The calculator can work out that you're saying you're doing it 4 times a year, and this is the number of repeated calculations, so that's all it needs to know. So then if you hit amount or future value, it says your future value of your 1,000 will be 15, 17 and all those decimal places. Now we always round it off because it's money, everybody wants to count their last cent, and this would be rounded off to $1,517.81. So you could quite easily do the calculation there on the Casio to check your work, unless you're in paper 1, in which case they might ask you just to display the formula and work with that. So do you get it? That's a very important financial application of exponential growth, where your growth factor is always 1, because you've got the 1,000 from before, 1 plus the decimal part, which represents a percentage increase that they're going to give you. So the idea of a multiplier there. All right, so let's come down, have a look at an example, a further example. This is another decreasing function example, or decaying one. A new car is purchased for $22,000. The value of the car all decreases. It's called depreciation, very important in accounting terms, at a rate of approximately 15% per year. What will be the approximate value of the car to the nearest whole dollar in 4.5 years? Well, can you see for a start that we can do this again? The amount that it's worth after T years is the original value times B to the T. It's depreciating every year, so this doesn't have to be adjusted. This in this application will just be years. And then we can say that's the original. This will be a fraction, won't it? Because it's going to go down. So our job is to work out what the fraction will be. What portion is left after each year? Well, let's work it out here. Here they are doing it 1 take 0.15. I do it a little bit differently here. Let's write it out. We lose 15% per year, so we have left 85% only. So each year we will times by 0.85, because if we times a value by 0.85, we only have 85% of it. So in other words, we're taking the 15% away from 100 and making it 0.85. They, over here in Pearson's, changed 15% to 0.15 and took 0.15 away from 1. Okay, so let's use our formula now. It says the amount after a certain time is the initial amount, and we were told the initial amount was 22,000, and then our multiplying factor, what we are going to reduce our figure by, or our depreciate or loss of money, is going to be 85%, and it's going to be for 4.5 years. So that will do it for us. So instead of saying that we've got just the 85% each time, we can do it all in one. Okay, so have a look at that. So you can see then that these are very powerful, these models, and you could then work this out on the calculator there at the end, and we get the value 10,588. Alright, so let's go down and have a look at some problems. Pearson's have got a number there for you, and I've got the fully worked solutions later on down here. So we'll just go down and have a look each of those sets of problems. I think that's it, 18. So you can pause that and work through them. And down below now, these solutions, 8 and 9. Just go to there and pause that. And 10. Just go a little bit further there for 10. Part of 11. Let's go to 11 now. Got a little bit of technology there. Right, then on to 12. Down to part B there. Let's just go a little bit further. Scrolling through. C. And finally D. We go back up and have a look at 13. We'll come down to 14 and 15. And the last three there, 16, 17 and 18. Alright, so look, have fun, build up your skill. It's a very important area. This exponential modelling, very powerful in both economic, financial terms and science terms as well, with the bacterial growth and the radioactive decay. Very, very important applications. So build up your skills there and see what you think. And we'll go on with a few more investigations and presentations in exponentials. So I'll catch you then, but for the moment, it's cheers from me.